In this video, we're going to learn to attack more complex Lewis structures with the same basic method that we outlined in the last video. I'm going to begin with a pair of gases here that are important in part because they make up roughly 98% of the atmosphere of the Earth. So you're basically just swimming in them at all times. N2 and O2 are in fact 2 of 7 elements that exclusively appear as diatomic molecules when they're in their elemental form. Just for your own edification, the others are H2 that you already saw a little while ago, I2, Cl2, Br2, and F2, essentially hydrogen, nitrogen, oxygen, and all of the halogens. These are not very stable as individual atoms. What makes nitrogen and oxygen a little different from the others here, though, is the way their Lewis structures look. And if we apply the method from last time for each of these, we'll go ahead and see what happens. Nitrogen has a total of 10 valence electrons for us to place in our eventual structure, because each nitrogen has 5, it being in group 5. By the same logic, O2 is in group 6. Each O atom has 6 electrons in the valence shell, so we've got a total of 12 to play with here. If I use the same method that we did beforehand, the skeletons are easy. Nitrogen to nitrogen, oxygen to oxygen. What we do next is then give everything an octet, and you'll notice that in each case, I wind up with the same number of valence electrons being necessary. Each of these are going to show me 14 valence electrons in my final structure. But when I go to do that fourth step, and I compare these numbers of electrons to the number I'm allowed, in each case, I say, uh-oh, that's not a good structure yet. I have too many electrons here. So here is the move that is going to turn a bad Lewis structure, for this reason, into the correct Lewis structure. If I can't make a good Lewis structure with single bonds because there aren't enough electrons to go around, the only way to solve that is to share more. So what I'm going to do is start making double or triple bonds. And just like a single bond is 2 electrons, a double bond will essentially be 4 electrons, and a triple bond will be 6 electrons that are being shared. So let's try this real quick. The basic move is this. I start with this oxygen. I say, I don't want 14 total electrons. I need to get down to 12. So I will make a new bond. Notice, however, that making the new bond now means I have more electrons, and it also means I don't have octets on either side. Count them up. 2, 4, 6, 8, 10 electrons around that O. Same thing around the other one. So the way to solve that is I knock off a lone pair from both sides. So goodbye, goodbye. Once that's done, notice I added 2 electrons, but I got rid of 4, which means I dropped from 14 total to 12 total. Now I count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that's a good structure. If I do the same thing with nitrogen, add a bond, get rid of a lone pair on either side, I reach 12. That's still not good enough. I have to get down to 10 according to the initial count, so all I need to do is the same thing again. Add a bond, get rid of the lone pairs, and this is a good structure now. Notice each nitrogen has its octet in place. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. But crucially, I have 6, 7, 8, 9, 10 total electrons. On this worksheet, I'd like you to work the step-by-step method for the more complex Lewis structures, just to kind of map it out. What you're seeing right here is step A, counting the valence electrons. Steps B and C are essentially being done here, making a skeletal structure and then giving everything its octet. And then these 2 bits are step D, counting the valence electrons used and deciding if it's okay or not. Don't worry about making it completely right if your answer here ends up being no. One last thing. You'll notice that I'm incorporating for the first time charges on a few of these. So we're making polyatomic ions like the ones that you saw in the nomenclature exercise on Wednesday. It's a very easy thing to give an entire molecule a 2- charge, or a +1 charge, or a -1 charge. The only thing it does is it changes the number of valence electrons that you're allowed to play with. And it does so the same way as it would if you were giving an atom a -2 or -1 or +1 charge. If I want to make an anion, I put more electrons into the pool. And I put in 1 for each charge. So if this is 2-, I'll add 2 more electrons. If this is 1-, I'll add 1. If I've got a positive charge, that means I have 1 fewer electron than what I would have expected for a nitrogen and 2 oxygens. So with that, pause the video and fill in as much of this as you can. Okay, let's rock. We should have 12 valence electrons on the CH2O, that is 4 plus 2 for the 2 hydrogens plus 6 for the oxygen. We should have a total then of 10 for CO, 4 and 6. By the way, if you have 6 and 8, make sure you're looking at group number to decide valence electrons and not atomic number. That sometimes trips folks up with C, N, and O. Next up with P2, also 10 because I've got 5 for each phosphorus and there are 2 of them. Now for the ions, carbonate is going to have 4 for the carbon, 18 for the 3 oxygens, 6 times 3, and then an extra 2 for the 2- charge, okay? And so that's going to give us a total here of 24 valence electrons to play with. CNO, I'm going to skip 2 for a moment. CNO is going to have 4, then 5, then 6, and then 1 bonus electron to give it the negative charge. So that will end up being 16. Lastly, NO2 plus is going to have 5 for the nitrogen, 12 for the 2 oxygens, but I've got to take 1 away for this positive charge. Remember, making a cation involves removal of electrons. Darn physicists. Okay, so that's going to also mean 16 here. For your skeletal structures, what I hope you decided to look at was the neediest atom in each case. So, good rule of thumb, if carbon is in your substance, it needs 4 electrons. It is probably your neediest atom. So we'll go ahead here and put carbon in like this. Carbon monoxide is easy enough. I just connect a carbon to an oxygen. Same thing with the phosphorus. And then over here, I've got carbon and 3 O's, nitrogen and 2 O's, carbon, a nitrogen, and oxygen. Again, for these, if you put them all in a line or at a right angle, doesn't really matter for now. If you put the O and the N on the opposite sides, doesn't really matter for now. The key is making sure the neediest atom is in the middle and everything else is attached to it. Okay, octet time now. So hydrogen, we know, only needs 2 electrons, so the H's are okay with a single bond. Carbon needs to have 8 total, so does oxygen, and at least as it's shown right now, the carbon is 2 short, because it's got 2, 4, 6. The oxygen has just 2, so it is 6 short. That's also the case for the carbon and the oxygen, and both of these phosphoruses here. In fact, when you do this method, pretty much any atom that is just connected to one other atom is going to need 6 electrons put on as lone pair electrons. The carbonate looks an awful lot like the CH2O, which, by the way, is formaldehyde. So we'll go ahead and put that there. And then over here, again, the oxygens are each going to need 6 more electrons. The nitrogen needs 4 more. Over here, the O and the N in cyanate need 6 more each. The carbon in the center needs 4. And now it's time to count. And if I count up all the electrons in formaldehyde, I've got 2, 4, 6 for the bonds, 8, 10, 12, 14. No good. 2, 4, 6, 8, 10, 12, 14. No good. 2, 4, 6, 8, 10, 12, 14. No good. How about this one? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. NO2 plus 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And in fact, that'll be the same down here. And both of those also problematic. So we are not okay. Not in any way, shape, or form. Every one of these is going to require some adjustment based on giving it fewer electrons, but still keeping its octet intact. So let's go to the whiteboard and give that a try. So here we have the results of our first round of things, but we determined that none of these have the right total number of electrons. In fact, this one is 2 electrons heavy. This one and this one are 4 electrons heavy. This one's 2 electrons heavy, and these two are 4 electrons heavy. So we need to do some serious elimination. If you think back to the situation with O2 and N2, what you may have noticed is that in order to eliminate 2 electrons, I basically need to make 1 new bond. To eliminate 4, like I did with nitrogen, I'm going to need to make 2 new bonds. And the big question becomes, where do I put those new bonds? Some of these are going to be easier to decide that for than others. For example, formaldehyde can only put a bond between the carbon and the oxygen, because think about the method. I'm going to place a bond and then delete electrons from either side. Well, hydrogen doesn't have any lone pairs for me to get rid of, so I can't possibly do it there. So formaldehyde's an easy fix. I put a new bond here, I get rid of a lone pair on carbon and a lone pair on oxygen, and if you look back at your worksheet, I now have 2, 4, 6, 8, 10, 12 total electrons, everything with its desired total number. Carbon, 2, 4, 6, 8 around it, oxygen, 2, 4, 6, 8 around it, and each hydrogen with 2. If I look at carbon monoxide or at diphosphorus, both of these are going to involve the same move because they are both 4 electrons heavy. They both are diatomic and have only 10 total electrons to play with. So in this case, I'm going to make 1 bond and delete those. I'm going to make another bond and delete these, and that's going to take care of my molecule. Looks an awful lot like nitrogen did, which also, I'll remind you, had 10 total electrons, 5 on each atom. Same thing down here with the phosphorus. 2 new bonds, delete these lone pairs for the first one, delete those lone pairs for the second. Notice that as long as you follow that particular rule, you'll never mess up your octets. And every time you do it, you drop your total number of electrons down by 2. Coming over to the carbonate ion, we're going to see a little something wacky here. So unlike formaldehyde, I've got options this time. I could put the double bond in between the carbon and any one of the oxygens. I'm going to pick one for now, but just know that if you did it on one of the others, you're not wrong. We're going to talk in the next video about how we deal with situations like this. So we'll go ahead and remove those lone pairs and put a double bond there for the time being, and this ends up being a good structure. All the rest of them as well have been recovered. Notice 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 total. Now each of these also had to lose 4 electrons, so I know I need 2 more bonds, but there are 2 ways I can do that. One is I could put a new bond on the left and a new bond on the right. So let's go ahead and do that with this example right here. In this case, I would put a bond on the left and eliminate 2 lone pairs, and then I can put a lone pair, or excuse me, a new bond on the right and eliminate those. And notice that's as far as I can go at this point because I've now officially run out of electrons on the nitrogen. I can't put any more bonds into this. The good news is I'm now down to 16 total. 2, 4, 6, 8, 10, 12, 14, 16. Alternatively, I could put both of the new bonds on the same side. So for example, I could go boom, boom, like I did with the diphosphorus or the carbon monoxide, and then just knock those lone pairs off and those lone pairs off. And that also gives me a resultant structure that obeys the octet rule and has the right total number of electrons. So this is cool, and this is cool. And in both of these cases, and for that matter, the carbonate, there is one other thing we would usually do in terms of how this is written, which is that we would put the whole thing into a bracket and add the charge out front. Main reason for this is you want to make sure when a fellow chemist sees your structure that they understand that you mean for this to be charged, because otherwise they just think you can't count valence electrons. So now we have a process in place that we can follow to take a group of atoms, bond them to each other, and make a valid Lewis structure. That is, one that satisfies the octet rule for all atoms and uses the right total number of electrons. What we're missing right now, though, is an ability to decide if multiple valid structures can be drawn for a certain molecule, which of them is the best structure for that molecule, or for that matter, if all of them are equally good and we need a different description. That is what's coming in our next video, which will discuss the topic of resonance.